second part of our webinar on reliability and life data analysis using Statgraphics Centurion. This is Neil Paulhemus. I'll be going through some of the procedures, some more procedures actually in Statgraphics that are useful for looking at reliability and life data. In particular, the procedures that involve one or more explanatory factors. This webinar will be a little bit shorter than the one we did last week. There was too much to do all the material in one webinar, so I broke it up into two. But this one will probably go only about an hour. I will invite you all, as I go through this material here, to use the feature of GoToWebinar that allows you to send us questions. We'll accumulate the questions during the webinar and try to answer them at the end. Okay. Well, this, as I said, is the second part of the webinar that deals with analyzing life data. Now, as a reminder, the type of data that we're considering here consists of lifetimes or times to failure. Data that measures how long it takes basically until some event occurs. Now, typical applications would involve estimating product reliability. You know, how likely is it that a product will still be working 3 years from now, or when at the end of the warranty period, or whatever you might be interested in. Another typical application, of course, is looking at survival times after different medical treatments. We have an interesting example of that type of data to look at also today. Now, as I also mentioned last week, there are about 7 different procedures in Statgraphics that are designed specifically for looking at life data. 4 procedures have to do with simply fitting a distribution where there are no explanatory factors. And in the last webinar, we looked at the life tables procedures, the distribution fitting procedure for censored data, the Weibull analysis procedure, and also some procedures for analyzing repairable systems. What we were doing in those cases was simply trying to take a set of life data collected basically under identical conditions and estimate the distribution of the lifetimes, the survival functions, the hazard rates, and so forth based upon the data. And what made the data interesting was, first off, rarely does that kind of data follow a normal distribution. And secondly, we often have censoring. Now, there are many cases where we do not have complete information on all the items that we've looked at or the subjects that we've looked at. But not wanting to throw away that data, it needs to be taken into account when we fit our distributions, fit our models, and so forth. The subject of the webinar today will be the 3 procedures summarized at the bottom of the screen. Procedures that can be used when there are explanatory factors. And we'll be looking at 3 procedures in particular. We'll be looking at the Arrhenius plot procedure, which is specifically designed for the case when you're doing an accelerated life test involving temperature, where rather than looking at the failure rates of your items under normal operating temperatures, where it may take a long time for the items to fail, you increase the temperature to levels where the items will fail more quickly than normal, fit some models, and then extrapolate the results to normal operating temperatures. We'll also be looking at the Cox proportional hazards models. That's a procedure that creates a non-parametric estimate of the survival function. similar to what the life tables procedure did in the case where there were no explanatory factors. And then finally, the life data regression procedure, where we have one or more predictor variables that we want to use to estimate the effect on the survival times. Okay, so in the second part of the webinar here today, I'm going to look at 3 examples. These will be examples 4, 5, and 6, counting from what we began last week. Example number 4 is going to be an accelerated life test. We're going to look at the reliability of certain devices employing an Arrhenius model. Number 5 will be a Cox proportional hazards model for cancer patient survival times. An interesting example where certain cancer patients were treated in 2 different fashions, and we're interested in knowing whether the treatment made a difference. And finally, we're going to look at example number 6, which is a general life data regression procedure, where we'll look at the reliability of capacitors as we change 2 different quantitative variables. Okay, well, let's jump in. And the first data we're going to look at, the first data set, is another data set from the excellent book by Meeker and Escobar having to do with the statistical methods for reliability data. They looked in this particular case at a certain type of device, and they called it device A. And what they were interested in knowing, of course, was how reliable these devices were, what the median failure times would be, what the probability would be they'd still be operating after some length of time, and so forth. Unfortunately, these devices rarely failed, or at least it took a long time for the devices to fail, at normal operating temperatures. So the experimenters decided to do an accelerated life test. They took some of the devices and ran them not at normal room temperature, but at 40 degrees centigrade. Then they took another set of devices and ran them at 60 degrees centigrade and 80 degrees centigrade. And, as is often the case at the higher temperatures, things failed more quickly. And what we'll be using in this case will be the Arrhenius model to try to estimate what would have happened at normal operating temperatures based upon what happened at the larger operating temperatures. Now, the basic procedure is going to be the following. We are going to employ something called an Arrhenius model. An Arrhenius model is often used to describe the relationship between the percentiles of a failure time distribution and temperature. And the Arrhenius plot in Statgraphics is based upon the equation that I'm showing you here on the screen, where basically the percentiles of the failure time distribution are assumed to follow a relationship that is basically an exponential relationship where E is raised to the minus something over T. In this particular expression, the way we do it in Statgraphics, T represents the temperature at which the experiments are done in degrees Kelvin. Now, if you don't remember, which I certainly don't usually, Kelvin is degrees centigrade plus 273.15. In the Kelvin scale, absolute 0 is 0. So if you need to go from centigrade to Kelvin, you just add 273.15. In this equation, K is something called Boltzmann's constant, which is 1 over 11,605. A and E are two unknown parameters that have to be estimated from the data. I suspect if you're a chemist, all this means a lot to you. From the point of view of statistical modeling, you can see that basically if you took the logs of both sides, you'd see that the log of the percentiles has a negative reciprocal relationship with T. Okay, as temperature goes up, the percentiles go down, so we expect increasing temperature to cause things to fail more quickly. Okay, now we're going to use this particular model, which is a very common assumption of how temperature accelerates failure times, to extrapolate data from an accelerated life test back to normal operating temperatures. And basically, it's going to be a step-by-step procedure, and I'll just summarize it before I go to Statgraphics and actually do it. What we're going to start out by doing is we're going to take this data and we're going to fit a Weibull distribution at each of the observed temperatures. Now, I've taken also an opportunity here to demonstrate for you a very important operator in Statgraphics called rep. Rep allows you to take a column of data and a frequency column and expand it out without having to type a lot of extra rows. For example, if I go back for a moment to this data set, you may see, if you look at the data set here, that there were a number of experiments done, a number of devices tested at 40 degrees centigrade. Actually, 100 devices. 10 of them actually failed. So I have a failure time of 1,298 hours, another failure time of 1,390 hours, and so forth. And the first 10 rows of the file have actual observed failure times. 90 of the items, however, had not failed after 5,000 hours. So what you see in row 11 here is an indication that at 5,000 hours, I still have 90 devices, and it's censored. If you look at the censoring column over here, you'll see a 1, indicating that that's a censored observation. We basically stopped the test after 5,000 hours, at which time 90 of the 100 devices were still operating. Well, rather than creating 90 separate rows, each with a 5,000 in it, I'll be using that rep operator to use this devices column to quickly expand out that data so I don't have to type 5,000 in 90 different times. Okay. Anyway, what we're going to do is we're going to fit a Weibull distribution at each of the temperatures at which devices were tested. And you'll see we'll come up with some Weibull plots. Okay, and I'll be going through this in just a minute. I just want to summarize what we'll do. We'll fit the Weibull distribution at actually 3 different temperatures. There's data at 40 degrees centigrade, 60 degrees centigrade, 80 degrees centigrade. We'll estimate what the median failure time was at each of those temperatures. Okay, what we'll call the P50 value, the 50th percentile. Okay. Then we'll go ahead, fit an Arrhenius model to the data at the 50th percentiles, and finally extrapolate the results back to normal operating temperatures. I thought I'd give you a highlight of what we're going to do before I go ahead and do it. Now, at this point, let's go over to Statgraphics and actually go through how we would do this. I've loaded up into the Statgraphics data sheet the data in a file called device-A. Now, as usual, we've provided on our website these data files, so you can try this out yourself later on. There is a column labeled temperature, and there are 3 different temperatures at which data was collected: 40 degrees centigrade, 60 degrees centigrade, and 80 degrees centigrade. The column called hours is the failure time or censoring time of each of the devices. And as I mentioned, devices is a frequency column that tells me how many devices correspond to each value of hours. And then finally, we have our normal censoring indicator here, 0 meaning that the data was not censored, that what you see in hours is a real failure time. On the other hand, a value 1 means that that's a right censored observation. And in fact, in this case, for example, 90 devices had not failed after 5,000 hours. Okay, now, to model the data, I'm going to go to the Describe menu to Life Data Weibull Analysis. And as I said, I'm going to use an expression called rep. So I'm going to type REP, rep, open parentheses. And then I'll type hours, common, comma, devices, close parentheses. That basically says take each value in the hours column and replicate it the number of times indicated in the devices column. And again, I'm doing this to avoid having to type lots and lots of 5,000s, for example, where I have 90 devices that were censored after 5,000 hours. Now, I need to do that rep operator also on whatever other columns I put in. So if I put in, for example, the censored column, I need to replicate that in the same way that I do the hours column. And where it says group, I'm going to put rep temperature, comma, devices as well. Okay, so I need to basically expand each column in the same fashion. Okay, I'll then press OK. And the Weibull analysis procedure will start up and will offer me a number of different ways to fit the model. I talked about this last week, in particular where it says estimation method. By default, it's decided to do a maximum likelihood estimate. Let's go ahead and take the default. And as far as tables and graphs are concerned, I'll take the defaults there too. Plus, I'm going to ask for critical values. Critical values is where you'll actually see the estimated percentiles. So let's go ahead and do that. Let's press OK. And here is the Weibull plot that was generated using a maximum likelihood estimation. And you'll see there are 3 curves here. There's a curve for 40 degrees centigrade, a curve for 60 degrees centigrade, and a curve for 80 degrees centigrade. And as you might expect, things fail more quickly at higher temperatures. Now, what we're going to do is we're going to look at the percentiles of this distribution, the Weibull distribution, at 80 and 60 and 40, and then extrapolate them to room temperature. Okay? Before I do that, though, the first time I looked at this particular plot, I was not that excited, I got to tell you, by how the maximum likelihood estimators handled particularly 40 degrees. I would have expected to see more parallel lines here looking at the cumulative distributions. I found actually that if I click the right mouse button, go to Analysis Options, and ask it to do a rank regression instead of a maximum likelihood estimator, that I got better results. This is actually what it looks like if you use rank regression, which basically means fit regression lines to each group of data here on the Weibull plot. You can see that actually the lines are somewhat more parallel. In particular, they don't cross up here at very high hours, which bothered me a little bit, although that was well outside where I've got the data. I also found out that I got a little bit better results, as you'll see in a minute, in the Arrhenius plot if I used the rank regression results. Okay. So I've decided, and if you download the notes from this seminar, you'll see I decided to go ahead with the rank regression estimates. Okay, now at this point what I'm going to do is I'm going to take the percentiles. In particular, let's take the median, the P50 value, the median failure time at 80 degrees, at 60 degrees, and at 40 degrees. And you'll be able to see those if you come over here and look at what Statgraphics in the Weibull analysis procedure calls the critical values. At 40 degrees, the median failure time was about 14,640 hours. At 60 degrees, it was about 4846, and at 80 degrees, it was about 1,261 hours. Those are the estimated median failure times at those particular temperatures. I'm going to take those P50 values now, put them into the Arrhenius plot, and extrapolate back to what would be a normal operating temperature. See, I've accelerated the failures here by increasing temperature, and now I'm going to use the results to extrapolate back to normal operating temperatures. Now to do that, I'm going to go back to my data book, go to tab B, and I've actually saved those percentiles in another file. There we go, where I've simply created a little data file with the temperatures in centigrade, 40, 60, and 80, and the P50 values that I estimated in that Weibull analysis a moment ago. Okay. Now what we're going to do is we're going to go ahead and fit an Arrhenius equation, an Arrhenius model, to these percentiles and extrapolate to normal operating conditions. To do that, we'll go to Describe, Life Data, Arrhenius Plots. And what it wants to know, it's going to be asking for two things. It's going to be asking for the percentiles, and I'll give it the column called P50, and it will ask for the corresponding temperatures, which are in C temp, only it wants temperatures in degrees Kelvin. So I'm going to have to type in here plus 273.15. Okay, so I've taken the temperatures in degrees Celsius and converted them to Kelvin. Press OK, and an analysis options box will come up and ask me at what temperature I want to make a prediction. Okay, now here what I would need to do is type in the temperature at which I expect these devices to typically operate. The default here is 300 degrees Kelvin, which would be about 27 degrees centigrade, which I believe is close to room temperature. So I'm just going to go ahead, press OK, and let the program extrapolate the percentiles to 300 degrees Kelvin. And what you can see here is you can see the percentiles, the percentile at 80 degrees Celsius, 60 degrees, 40 degrees. You'll see the fitted Arrhenius model, by least squares. And you can see that this fit is actually pretty good. And then the extrapolation up here to 300 degrees Kelvin gives me an estimate, you can see this up at the top, of a P50 value of about 40,000 hours. So using the Arrhenius model, and it is an assumption that the Arrhenius model is the appropriate model, but if you make that assumption, which is a very common assumption when you're dealing with temperature, then I would predict median time to failure at 300 degrees Kelvin to be about 40,000 hours. And actually, Meeker and Escobar comment that the Arrhenius model, that if you don't use an Arrhenius model when you're accelerating the temperature, that often people suspect your data rather than the assumption of the Arrhenius model. I guess it's that common to use in practice. Well, that's in a typical example where we've accelerated the failures by changing the temperature, and we're using the Arrhenius model to fit, in this case, the percentiles at P50, although we could have chosen some other percentiles and fit those instead. In this case, though, have fit the P50 values and extrapolated them to room temperature. Fairly simple plot, but very, very useful if you're dealing with that kind of data. Okay. Let's go back to the PowerPoint slides now and take a look at my second example of the day. And this one is going to have to do with Cox proportional hazards models. Okay. Now, the data I'm chosen for this example comes out of a book by Collett called Modeling Survival Data in Medical Research. And it's typical of data that might be collected to determine whether some medical procedure increases the survival times of patients that were given that particular procedure. Now, the example is in a data file called nephrectomy. And what it is the survival time of a selected set of patients. Survival time actually recorded in months. These were all patients who had been diagnosed with some sort of kidney cancer. Okay. Now, some of the survival times are actual survival times. The patients, unfortunately, died after a certain number of months. Some of the times are censored. So you can see, for example, row 8 has the value 104. So that patient had survived 104 months and did not at that point die of kidney cancer. They may have died of some other cause or may have left the study, but that is a survival time. I'm sorry, a censored time. So some are actual survival times, some are censored. The column nephrectomy is an indicator variable. It contains either a 0 or a 1 to indicate whether the patient had a nephrectomy. Now, as I understand it, a nephrectomy involves removing all or part of a kidney. Some patients did not have a nephrectomy, some did. What we're interested in, and at least one of the major things we're interested in, is knowing whether or not having nephrectomy affects the survival time. And hopefully having nephrectomy increases the survival time, but that's something we'd like to find out, obviously, from the data. There's also a column over here called age. In addition to nephrectomy, which indicates whether or not the patients had the nephrectomy, the patients have also been divided into different age groups. Age group 1, age group 2, or age group 3. 1 indicates a younger patient, 2 was, I believe, an older patient, and group 3 was even older. Okay, and they were interested in knowing also whether the effect of having a nephrectomy was the same or different for the different age groups. Now, the model that we're going to use to model this particular data is called the Cox Proportional Hazards Model. It's a semi-non-parametric model. Non-parametric in the sense that we will not assume any particular distribution for the failure times. We're not going to assume a Weibull distribution or a log normal distribution or anything like that. So in this sense, it's going to be similar to the life tables procedure that we did last week, in that we're going to estimate the hazard rates at a particular combination of the x's based solely on the times at which we saw either failures or censored observations. With respect to the effect of the x's, and the x's are going to represent whether or not you had a nephrectomy and what your age was, we will assume a parametric model for the x's. And that model is an exponential type model where you have the exponential function at beta 0 plus beta 1 times x1 plus beta 2 times x2 and so forth. So the relationship of the x's is parametric, but the failure time distribution itself is non-parametric. So some people would call it a semi-non-parametric model. Okay. Now, what I've written here is the general form of the hazard function. You may remember from last week I mentioned the hazard function and interpreted it as being the propensity to fail after a certain length of time. Okay? Some people might call it the instantaneous failure rate, but basically it tells me how likely I am to die, in this case, having survived up to some point in time t. Now, in the Cox Proportional Hazards Model, we assume that the basic shape of the hazard function is the same regardless of what the value of the x's is, regardless of whether you have nephrectomy or not, what age group you in or not. The basic shape of the hazard function is going to be the same. However, the hazard function at a particular combination of the x's will be proportional to the hazard function at some baseline value of the x's. That the hazard rate changes proportionately based upon what the x's are, and in particular based upon this function here of the x's. Okay, so what's going to happen is that hazard rate, if you start at some base level, and in Statgraphics the base level, as you'll see, is when all the x's are 0, it's going to move up or down according to the combination of the x's. Okay, so that is the assumption. It's called a proportional hazards model because the hazard at any particular combination of x is proportional to some baseline value. Okay, now to use it, we will go to Statgraphics and analyze and select the Cox Proportional Hazards Model. Now, let me go back to Statgraphics. Let's close off this particular data file that we were working with before and open up a data file called, you guessed it, nephrectomy. Okay. All right. There are 4 columns in this data file. One is called survival time, one is called censoring, one is called nephrectomy, one is called age. Scroll down. First time, 36 observations. Now, to fit the Cox proportional hazards model, we'll go to Relate on the top menu to Life Data. Under Relate Life Data, there are 2 selections. There's the parametric models procedure, which I'll look at in a few minutes, and then there's the Cox proportional hazards model that we're looking at the moment. So let me select the Cox proportional hazards model. It'll open up a data input dialog box. Now, where it says dependent variable, I'll put in survival time. Where it says censored, I'll put in the column containing the censored indicators, 0s or 1s. And now, in a manner similar to a lot of our other regression procedures, I can add explanatory factors of 2 different types. I can add quantitative factors, or I can add quantitative categorical factors. Now, in this case, both nephrectomy and age are indicator variables. They indicate the group that each particular survival time belongs to. If I knew the exact ages of the patients, I suppose I could put them in as a quantitative factor. But since they were grouped in Collett's example into 3 different age groups, I'll have to put it in where it says categorical factors. Okay. The next dialog box I'll see will be a analysis options dialog box. And I can ask here for either a first order or second order model. In the case of a first order model, the observations will go in just basically as main effects. If I ask for a second order model, in this case it would potentially put in an interaction term between nephrectomy and age. In Collett, he just did a first order model, so let's go ahead with the defaults. As far as the output, I think I'll ask for the analysis summary, the survival function, and also add in the hazard function. Okay. So let's go ahead and do OK, and at this point we'll see the results of the Cox proportional hazards model. Now, what's of particular interest here initially will be the statistics that pop out. You'll see it says there were 32 uncensored values. Those are real survival times. And there were 4 right-censored values. So for whatever reason, 4 patients left the study before they died of kidney cancer. If you look at the regression model, the section here that says regression model, there were 3 X's added to the model. Each of those X's was an indicator variable to distinguish between the groups. Now, in this case, the baseline group was the first value of nephrectomy and the first value of age. So the baseline group would have been patients that were not given a nephrectomy and also were in age group 1. It is added, as we would in a normal regression model, indicator variables to differentiate between the groups. Now, in the case of nephrectomy, you'll see that where it says estimate, that's the beta, the coefficient on nephrectomy is minus 1.5. Minus means You have to, I have to remember what minus means. Minus means that if you were given the nephrectomy, then the hazard rate went down. Yeah, that had to be good. Yeah, if you were given the nephrectomy, if you had an operation to remove all or part of the cancer, it reduced the hazard. We'll see this in the graphs, but numerically, and you can see the equation actually down in the section on the Stat Advisor, having a nephrectomy reduced the hazard. And you can see also down here where it said likelihood ratio tests that the p-value on nephrectomy is quite small. It's 0.009. So even at the 1% level, that reduction in the hazard was statistically significant. With respect to age, we needed to add 2 indicator variables for age because there were 3 groups. Age 2, you can pretty much see the coefficient is 0.01. That means that group 2 was very little different than group 1. On the other hand, if you look at group 3, there was quite a substantial, it appears, increase in the hazard if you were in group 3. So if you were in the oldest group of patients, the hazard rate went up quite a bit compared to the younger patients. On the other hand, if you want to look at the likelihood ratio test, the p-value is 0.09. Now, that's significant at the 10% level, but not significant at the 5% level. So there could be some question about the statistical significance of age, although it certainly is at the level that it would be somewhat interesting at least. Now, as far as the graphs are concerned, let's click over here at the top right and look at the estimated survival function. Now, the estimated survival function here will be plotted at different levels of any one of the factors, holding all the other factors constant. So in this case, for example, we're looking at the survivor function for patients in age group 1. That's the youngest group. The blue line is the survivor function for those not given a nephrectomy. The red line for those that were given a nephrectomy. And you can see a fairly substantial shift to the right for the patients that were given the nephrectomy. In fact, if you look at where the survival function is 0.5, which would be the p50 value where the probability goes below 5, there's about a 2-year increase in the p50 value having had the nephrectomy. Okay, so it's really quite substantial, at least for age group 1. Let me right-click, go to Pane Options. Pane Options is where you can select what factor you want to plot versus and the level of the other factor. Let's look at it for age group 2. That's still pretty substantial for age group 2. How about age group 3? Well, there's still a change for age group 3. I think you'd find that it wasn't quite as substantial in effect. A little bit less, perhaps, for age group 3 than for the other age groups. But for any age, it appears that there was definitely some benefit of having the nephrectomy. Now, you can also go down and look at the second graph. The second graph shows the estimated hazard function. The hazard function is, again, the propensity to fail given you've survived a certain length of time. Now you can see a couple of things here. You can see first off the non-parametric nature of the hazard function. Had we assumed a Weibull distribution or something like that, we would have gotten nice smooth curves for the hazard function. Here you're getting large estimates of the hazard in the vicinity of the actual times when people died. You can also see, though, the proportional nature of the hazard rate estimate. The shape for nephrectomy 0 is the same as the shape for nephrectomy 1. They just change in a proportional manner. Hence the word proportional hazards. So that's gives you an idea actually of the mathematics, the mathematical models, or lack thereof, if you like, with respect to the actual lifetime distribution that we assume when we do a Cox proportional hazards model. Okay. Well, I thought that was an interesting example and a good example of some medical data. Now, the final example I want to look at today is going to use the life data regression procedure. The life data regression is similar in a sense to the Cox proportional hazards model in that we'll assume a particular functional form for the effect of the X variables on the survival times. But we're going to go a little farther than that. We're going to assume that there is some particular distribution that's appropriate for the survival times at a particular value of X. For example, we may decide, as I will, to pick a Weibull distribution. Okay? So this will be more similar to the Weibull analysis than it was, for example, to life tables, which was non-parametric. This will be a completely parametric approach. Now, it's also going to be quite similar to what we do when we do a standard regression analysis. Okay, only we're not going to assume a normal distribution. We're going to pick typically some other distribution. And we're also going to allow for the possibility of censoring. Those are a couple things that always distinguish life data from other types of approaches. Now, the example here comes again from the book on Statistical Methods for Reliability Data, and it's data having to do with failure times of capacitors. In this case, an experiment was designed to try to determine what the effect on the failure rates was of changes in voltage and changes in temperature. And it's actually a factorial design. I believe it's a 4×2 factorial design. The experimenters took 4 levels of voltage, 2 levels of temperature, and tested capacitors at all 8 combinations of those factors. And where it shows the hours, that's the number of hours before a particular capacitor failed. Now, there's no censored column in this particular data because there was no censoring. All of these are actual failure times, although there clearly could be a censored column if we decided to end the test before all the capacitors have failed. Okay, so think of this as basically being a 4×2 factorial design where you're measuring the hours to failure. Now, what makes this different than just going ahead and analyzing it the way we would in the experimental design wizard is the fact that we're not going to assume that the failure times follow a normal distribution. And in particular, the life data regression procedure allows you to select amongst 7 different distributions to characterize the failure times. we can select between a normal distribution, a logistic distribution, a smallest extreme value distribution, a log normal, a log logistic, a Weibull, or an exponential distribution. And depending upon what distribution you pick, the procedure will fit either a location scale model, which is the type of model that you're used to if you're doing a standard regression, or a log location scale model. Now, as in all the standard regression procedures, we will assume some either first or second order model relating the x's to the response. And here you see it's written as you would in the case of a normal distribution. The mean is equal to beta naught plus beta 1 x1 plus beta 2 x2. Well, we're writing it as mu. It is the mean if we assume a normal distribution. Otherwise, it's a central value, which we'll call simply a location parameter. Okay? The x's in this case will be voltage and temperature. In addition to the equation that relates the x's to that central value, there's also a scale parameter called sigma. Sigma affects the spread of the lifetime distributions around mu. Now, if we decide to pick a Weibull distribution or a log normal or log logistic, then we'll be using what's called a log location scale model. And that's what I've actually written down for you here. In a log location scale model, we would assume that the cumulative distributions of the lifetimes follow either a log normal or a log logistic or a Weibull distribution or exponential distribution, which means that if I take the log of the lifetimes, subtract mu, and divide by sigma, that follows some common distribution. As in the case of a general regression procedure where you assume that although you may be changing the x's, which moves the center of the distribution around, the spread remains the same. We're making a similar assumption that the shape of the distribution remains the same except for the location parameter, which is a function of x. Okay, now, and incidentally, if we assume that the lifetime data, the lifetimes follow a Weibull distribution, then the logs of the lifetimes follow a smallest extreme value distribution. There's a good discussion of this in Meeker and Escobar, of these types of models. But basically what happens if you assume that the lifetimes are Weibull, but you take the logs of the lifetimes, then the logs of the lifetimes follow a smallest extreme value distribution. Okay. Okay. The same way, you know, if you take log normal data, take the logs, they follow a normal distribution. Okay. This is what we're going to fit. Now we're going to fit it using a life data regression procedure. So let's go back to Statgraphics. Let's close off this particular data file and open up a data file called capacitors. There it is. This file consists of 32 observations. At each combination of voltage and temperature, And remember, there were 4 voltages and 2 temperatures. It's a 4x2 factorial design. They tested 4 capacitors. So we have 4 times 2 times 4, a total of 32 failure times. Now, there could have been a censored column. There isn't in this data file because none of the data were censored, but if there was censoring, I would also have a column out here called censored. Okay, to fit a regression model here, I'm going to go to relate life data, but this time pick parametric models. Now you'll see that the data input dialog box looks the same as it did in the case of the Cox proportional hazards. I need to put in the dependent variable, which was hours. Had there been censoring, I would have put in a censored column. And then we have fields for putting in the quantitative variables or the categorical variables. Now in this case, both of the variables are quantitative. So I'm going to put in voltage and temperature where it says quantitative. Okay. Let's go ahead and press OK. Second dialog box you'll see is the analysis options dialog box. And here we can ask either for a first order model, which would just have voltage and temperature by themselves, or we could ask for a second order model. A second order model would typically contain things like voltage squared and also interactions, voltage times temperature, for example. I'm actually going to fit a second order model in just a moment, but I'm going to start with the first order model. In addition to picking the type of model, I need to pick a distribution. And since the Weibull distribution is so common for failure times, I decided to go ahead and just take the Weibull distribution. Let's go ahead, press OK. And now we get to pick some tables and graphs. And I think I'll pick, in addition to the analysis summary, the percentiles table. In addition to the plot of the fitted model, the percentiles plot. You can see there are also residual plots, a lot of the same things you'd find in the other regression procedures. Let's go ahead, press OK, and now it's going ahead and fit the model. Now let's take a look at what it's done. In particular, let's look at the analysis summary in the upper left. It says there are 32 uncensored values, no censored values. It's fit a model involving a constant, beta 0, a term beta 1 multiplying voltage, a term beta 2 multiplying temperature, and a value for sigma. And then you'll also see that it assumes a Weibull distribution. Looking at the likelihood ratio tests, there's a very, very small p-value on voltage. So voltage is actually quite significant. The p-value for temperature, on the other hand, 0.08, significant at the 10% level, but not at the 5% level. I'm quite certain that voltage has an effect. Temperature, on the other hand, is not significant at the 5% level, but it's close. Now, if you want to visualize what happened, let's go up here and take a look at the percentiles plot, similar to what we saw in the Cox proportional hazards model. What you see along the bottom x-axis here is the voltage. As in many of our multi-factor models, we're plotting the survival probabilities, or in this case, the percentiles of the, it's not the probabilities, it's the percentiles in this case, the percentiles of the lifetime distribution as a function of one of the factors with the other factors held constant. So this is actually a plot of the 5th percentile, the 50th percentile, and the 95th percentile of the Weibull distribution as a function of voltage at a particular temperature. Okay? So the way I would interpret this, pick a voltage. Let's pick 350 volts, 175 temperature degrees. Okay? The lowest percentile, which is the 5th percentile, is at about 150 hours. So at this particular combination, 350 volts, 175 degrees, about 5% of the items will fail by 150 hours, about 50% by 300 hours, and 95% will fail by 500 hours. Okay. If you reduce the voltage, the percentiles go up, which means that the items don't fail as quickly. And voltage, you see, does appear to have quite a significant effect. Now, at this point, I decided, since voltage was not statistically significant, that maybe I should try a different model. If I right-click and go to Analysis Options, I could decide to fit a second-order model. A second-order model will typically put in quadratics like voltage squared and temperature squared, and also interactions like voltage times temperature. Unfortunately, if I ask for a second-order model here and press OK, an error message comes up. It says error, factor BB is a linear combination of other variables. The problem here is that temperature, and BB refers incidentally to temperature squared. Temperature has only 2 levels. If you have only 2 levels, you have to assume a straight line. You can't add a second-order term. To get rid of that, I need to right-click, go to Analysis Options again, but before I fit, press the Exclude button. And if I double-click on temperature squared, I can get rid of temperature squared, at which case it'll go ahead and fit a model for me. And if you look at the model that it's fit down at the bottom here, it now involves voltage, temperature, voltage squared, and voltage times temperature. Okay, that last term, voltage times temperature, being an interaction. Now, take a look at the likelihood ratio tests. All of a sudden, voltage doesn't have a small p-value anymore. Neither does temperature. Voltage squared, on the other hand, does. Voltage times temperature doesn't. Now, because of the fact that these variables are not centered, I didn't pick -1s, 0s, and +1s, for example. The estimates of all of these parameters are quite correlated with one another. And the next thing that I would probably do, seeing I have a lot of insignificant terms, is to pull out the least significant term. And you can see that voltage times temperature has a p-value of 0.8792. That's not even close to significant. So let me go ahead and basically remove that interaction. Let's right-click, go to Analysis Options, go to Exclude. I'm going to also double-click on voltage times temperature to get rid of it. And now I've got myself a nice model. If you look at the likelihood ratio tests again, now I have a model with simply voltage, temperature, and voltage. All the p-values are actually well below 0.05. So all the terms that are remaining here are actually statistically significant at the 5% level. Now, it doesn't have a huge effect on the percentiles. You can see there is the same percentile plot. There is, though, I believe, a little bit more curvature in voltage, with respect to voltage, than there was before. Yep. Oh, and incidentally, there is one other plot. This is a plot of the percentiles, the 5th, the 50th, and the 95th percentiles, as a function of voltage with temperature held constant. If you like, there's also a percentile plot. That was the second one that I'd asked for, where you pick specific combinations of your x's. In this case, 275 volts, 175 degrees. And it will plot for you the percentiles of the failure time distribution with 95% confidence limits. Okay. So for example, if I was to look at, let's say, the 80th percentile at this combination of the factors, the 80th percentile is around 550 hours. Looking at the 95% confidence limits, however, that 80th percentile could be as low as this value here. And maybe I should bring up the crosshairs to do this more accurately. Bring up the crosshairs. Could be as low as about 474 or as high as about 671. Now you can do that interactively on the graph. There's also a table. If you really want to know what they are accurately, here is a table of the percentiles at 275 volts, 175 degrees. And that 80th percentile I was just trying to estimate here, the estimate is 562 hours for the 80th percentile. 95% limits are 472 to 668. So one of the primary outputs of the life data regression procedure is these percentiles, which you can find for any given combination of the factors. Okay, well, those are the three examples I wanted to talk about today. As usual, we have posted the slides of my presentation on the webinars page at www.statgraphics.com. I've also posted each of those sample data files for you to try. Sometime this afternoon, we'll put up a recording of the webinar. And now it's time for questions. So I'm going to escape off of my PowerPoint slides, take a look at my GoToWebinar control panel, and see whether I have any questions. Well, I don't have any questions yet. If you do have some questions, go ahead, type them in, and I'll try to answer them in a minute. There was one question left over from the last webinar having to do with the bathtub curve that I did want to make a couple comments on. And let's see if I have, yes I do, another slide here. The bathtub curve shows a very common hazard function for a product over its entire lifetime. It's common to divide the lifetime of a product into 3 periods. This plot, incidentally, comes from the NIST site, NIST.gov, National Institute of Standards and Technology. They nicely plotted out, although you can find these also in a lot of textbooks. Typically with a bathtub curve, what you do is you divide the lifetime of the product into basically 3 periods. In early failure period, where due to manufacturing defects, in the case of manufactured products or birth defects, for example, you start out with a lot of early failures. Those items that were not manufactured properly will tend to fail quite early, hopefully during the warranty period, or hopefully before you even ship them. So you've got a period of a fairly high failure rate early on. After a while, once all the failures due to the manufacturing defects have occurred, you get into what's called the intrinsic failure period. The intrinsic failure period is a period that's typically characterized by a fairly constant failure rate at a rather low value. And then once you reach the typical lifetime of the products, you get into the wear-out failure period where the hazard rate then starts to go up. There was some discussion and some comments after the last webinar that certain distributions like the Birnbaum-Saunders distribution might be able to characterize this entire bathtub curve. I don't think that's the case. I was not able to find any good instance where any single distribution would be appropriate for both the early failures and the wear-out failures, with the exception of some rather elaborate distributions that people had invented recently to try to model all of this. But certainly none of the parameters that none of the distributions that you'll find in Statgraphics or a typical statistics package are going to model both early failures and wear-out failures. Rather, if you do want to fit distributions to both the early failures and the wear-out failures, typically that's done with 2 separate distributions. One to model the early failures and one to model the wear-out period. If anyone feels differently about that, please let me know, but I was not able to find any case where any single distribution could model the data in both the early failure and the wear-out failure period. Okay. All right, let's see. We do have one question here. How to choose the proper distribution for failure time for a parametric model? That's a pretty good question. Head here, right, and assume a Weibull distribution. We do have some other diagnostic tools, particularly graphical tools, that could be useful in seeing if the assumed distribution makes sense. Now, let me ask for a couple of these other plots. One's called the percentile probability plot. Well, that's not going to be helpful. What we need actually is a way of looking at the residuals from the model. As in most cases, what you're going to need to look at, as in most regressions, you're going to need to look at the residuals to see whether they behave in the manner that you expect. That was an interesting question. I hadn't actually looked at any of the residuals here. Let's see what the residual probability plot is. Okay. There we go. this is a nice way to assess, in particular, whether the Weibull distribution was appropriate. What we've done here is we've taken the residuals from the model. That's the difference between what the model would have predicted for the failure times and what actually was observed. Each of those residuals has been standardized, basically, to take out any difference in the sigma, and standardized in such a way that we can plot them on a single Weibull probability plot. And if the Weibull distribution is appropriate for the data, you would expect the residuals, the standardized residuals, to fall approximately along a straight line. And that's almost as good and pretty a Weibull probability plot as I could ever expect to see. Those points obviously fall nicely along that probability plot. Some authors say, actually, to judge whether that's good or enough, you take a thick pencil, lay it across the plot, and if it covers up all the points, that's a pretty good fit. Anyway, that probability plot is one of the tools, the best tools to use, at least to visually judge goodness of fit. And depending upon what distribution you pick, if you'd assumed a normal distribution, it would be a normal probability plot. Having assumed a Weibull distribution, it's a Weibull probability plot. But it'll give you whatever the appropriate probability plot is. There's also the, let's see, observed versus predicted. This is a plot of the observed failure times versus the predicted failure times. Now, that's not as much a test of the distribution as it is of the model. And actually, you might, if you looked at these points, the high predicted points, you might believe that, in fact, there was some curvature here. Now I'm actually wondering whether putting voltage squared into the model was a good idea or not. It certainly came up as statistically significant. Let me go back to the first order model just for fun and see what it does to this plot. Okay. That's actually, it looks a little bit nicer. These are the observed failure times versus the predicted failure times. That's a pretty decent way to judge the adequacy of the model. That's where we would go in a normal regression to see if we needed to put in quadratic or nonlinear terms. Interesting. What probability, Weibull probability plot, by the way? Where's the Weibull probability plot? Here. Still looks good, even with the first order model rather than the second order model. So I would definitely suggest using that probability plot as a way to judge whether you picked a reasonable distribution for the lifetimes. Okay, there's a second question. Due to equipment availability, our QE department environmentally tests at 240 hours, typically without any failures. I question this approach. Can you use any of these models to predict life of a product without any failures during testing? Well, I don't think we're going to be able to fit any parametric models if we haven't seen any failures. I'm not sure whether we could estimate a non-parametric model. I doubt that either. You could make an interesting argument, though, about the probability of failures using just something like a Poisson distribution, failed versus not failed. I mean, if we know that you tested 100 items and there were no failures after 240 hours, there are ways to to give you some information about what's the probability, at least an upper bound on the probability that any item would fail at 240 hours. That would be essentially a tolerance, some sort of a tolerance limit for the Poisson distribution. Yeah, I don't think there's any way to estimate like the median failure time if you've tested a bunch of items for 240 hours and you haven't seen any failures. But you certainly could put an upper bound on the probability of a failure having seen no failures after 240 hours. Trying to remember where in Statgraphics would be the best place to do that. We have tools. We have distribution fitting. There are some, well, let's see. You had no failures after 240 hours. It's like a tolerance limit for a rate. Let me see. Describe categorical data hypothesis tests. Okay. We can, for example, I believe if we have no failures after 240 hours, let's say we tested 10 items and saw no failures. Okay, so I've got a sample rate, no failures, and let's say I tested 10 items. I believe we can do some confidence intervals. When we have a 0, and let's do a greater than to do an upper bound. Okay, oh, that gave me a lower bound. Let me do an upper. Maybe I have to hit less than. There we go. This is probably the best I could do. Let's say I saw no failures in 240 hours testing 10 items. Then I can tell you with 95% confidence that the worst the failure rate could be is 0.3 failures in 240 hours. So we could actually use the hypothesis test procedure to give an upper bound on the failure rate at 240 hours, but we're not going to be able to estimate mean time to failure or anything like that. Okay, just to review that, the question was, suppose I tested a certain number of items, and I just assumed 10. For 240 hours, there were no failures. What can I say? Well, one thing I can say, I want to describe categorical data hypothesis tests. Okay? Told it I wanted to estimate a Poisson rate. I had a sample of 10 items. I saw 0 failures. Okay? Then as for an alternative hypothesis of less than, I could say with 95% confidence that the overall failure rate in 240 hours is no more than 0.3 failures per 240 hours. I don't think there's much more I can say without at least one failure, which is why, again, we started with, for example, some accelerated life testing with my example of the Arrhenius plot early on. I had to make things fail so I could extrapolate back to normal conditions to get a reasonable estimate of something like the P50 value. You all are making me think on my feet today. Okay, I don't see any other questions, so thanks again. I'm not sure what the next webinar is going to be, so if you have some suggestions, if there are things you'd like to hear, be sure and let me know. I definitely want to schedule one in May, so if there's a topic you'd like me to talk about, let me know. Okay, we'll be posting the webinar on the website sometime this afternoon. Thanks again.